started. We got to fly through chapter 14 today, maybe get to chapter 15, not sure. But got some announcements to get us started for next week, because next week is midterm 1. I'm going to ask you to test your device using the Lockdown Browser test quiz. I know most of you have come from Chem 1210, but those of you who have not taken chemistry here, we do take our exams under Respondus Lockdown Browser because we administer it via a Carmen quiz. Everything is multiple choice, numerical input, or like pull down menu, but you will do it in a proctored setting under Respondus Lockdown Browser. We have a test quiz open for you to test your device. That device can be an iPad, a laptop, whatever. But that needs to be tested as soon as possible. Even if you took this 1210 in the spring, do test your device again to ensure that it works. The password to this test quiz is test. And you'll see the different question types, and you'll be able to explore Lockdown Browser. There is an embedded calculator in there in case you run into trouble and need to use a different calculator. There is one there that you can look at, and you can test out like the flagging functions and all of that. So if you don't take this test quiz by this weekend, I'm going to start sending angry emails out because I want to make sure everyone tests in recitation successfully in our first midterm. With that, all 4 practice midterms are already posted, and that equation sheet is published as well. So you have lots of materials to study from this weekend. I really highly encourage you to utilize all 4 of these practice exams. That's almost 100 questions for you to familiarize yourself with, because it's the practice exams. Those types of questions are most likely what you'll see on the actual exam. So every year I always do review sessions before every midterm. So on Monday, I only anticipate like the last 20 minutes of class. I'll do some in-class midterm exam review. But what I want to do is just convert my office hour, that's typically after class. I'm just going to convert that into a review session that we'll just do in this classroom. So we'll just take a little break after lecture, come back, and we'll just do a review session. I'll make the packet for this review session, and so I'm going to Zoom it, and I will also record it as well so you can have access to it before your midterm the next day. I will point out, I write the exams. I write the review session packets, so it's in your best interest to listen to what I have to say at the review session. Okay, so yeah, Monday office hours will convert to a review session. If you have like lab or like specific questions, I'll leave time for us to do that either before the review session or afterwards. And then finally, our first big homework sets are going to be due this Monday, and these homework sets are in preparations for your midterm exam. So all of chapter 13 is due by Monday, and then only chapter 14 part 1 is due on Monday before class as well. But I'll remind you that any individual questions submitted after the due date, those are only the ones subject to the penalty. Any questions you complete prior to the due date, you have the opportunity to earn full credit. It's just the individual ones answered late get that small penalty. Okay, so those are your announcements. Do that Lockdown Browser test quiz. I want to make sure everyone tests and doesn't have technology issues at that midterm in recitation on Tuesday next week. Okay, so we're going to continue on with chapter 14. The next 2 sections are covered on midterm 1. While the last section will be on midterm 2, and I'll indicate when that transition happens. So on Wednesday, we looked at an example of how temperature affects reaction rates. What we see is that temperature, as you increase temperature, reactions always get faster. And we'll look at why in a little bit. And the reason is, if we throw back and think of collision theory, reactions only happen when particles collide. And so if we increase the temperature of our sample, more collisions are going to happen. And so we'll look at the concepts behind that. And so the reason reactions get faster when we heat them up is because your rate constant, that value is changing. So before, when we were looking at rate laws and stuff in the previous sections, if you were given a rate law, we could see, oh, if you increase the concentration of your reactant, typically rate increases. But now we're looking at a new way to increase reaction rate. Okay, let's change K, the value of that rate constant, and we do that by changing the temperature. So increasing either of these terms will increase rate. We already looked at increasing concentration or changing concentration. Now we'll look at that rate constant. Okay. So the reason that reactions go faster at higher temperature, one is because temperature is related to the average kinetic energy of your sample. When we have a gas sample, all those particles, they're not all moving at the same speed. Instead, we have like this distribution of speeds. Every particle is unique. But what that temperature tells us is the average kinetic energy, the average speed of all of those particles. So what we see is the distribution of molecular speeds is dictated by a Maxwell-Boltzmann distribution. It kind of looks like a Gaussian curve with a long tail on the end. And so what we see is at low temperature, we have a distribution of molecules going slower. But if you heat up that sample, more of those particles are going to be going faster, that the shape of that distribution shifts to higher speeds. So again, because every particle is unique and all gas particles are not moving the same speed, but we have a distribution kind of pushing to higher realms when we increase that temperature. And so what we see is, why this matters is because with temperature, when we're changing your temperature, we're increasing where that average lies. What we change is the energy associated with that system, and that energy is related to the energy curve of the reaction. So low energy reactions have, or low kinetic energy, low temperatures, doesn't have enough energy to overcome this, what we're gonna talk about here soon is an activation energy. Versus if you have a really hot sample, so this is my hot sample, here's my cold sample, there's a lot of kinetic energy present in this sample, enough energy where all those particles can overcome this, this activation energy hump, this hill. And so this is why reactions go faster at higher temperatures. There's just more available energy for us to overcome this activation energy. So numerically, how we relate these things, how we relate reaction speeds, activation energy as temperature, is through the Arrhenius equation. So this equation we give to you, though I'll point out we never actually have you use this equation for anything. We never have you calculate, like put in numbers in this equation. We use a different equation. But what this equation tells us is some trends. That rate constant, K, from that rate law is related to a couple things. A is a frequency factor. This accounts for the efficiency of the collisions of the actual particles. It's a constant based upon what reaction is happening. But what's more important here is this E term, this exponential term. E to the, and then we have this fraction, the negative activation energy for this reaction. So our activation energy is how high that first hill is. So I should point that out, that basically, if you go from reactants to products, it's that minimum amount of energy, that hill you have to clear in order to get to the product side. So here is your activation energy for this reaction. How big is that hill you have to get over? So we see that rate constant is related to E to the negative activation energy over R. This R is the energy version of R, 8.314 joule mole Kelvin, because we're talking about activation energy. The R we use should be in the energy term. And then finally, there's a temperature in the denominator in that exponent. So what we see here is that as energy or temperature increases, this whole fraction becomes a smaller negative number. All right, and so if you have a small negative number taken to the exponent, you actually get a bigger number come out. So what's important in this equation is the trends that come out of it. How can we change K? A is a constant for the most part, so that doesn't really change. But what we see here is activation energy can change for a reaction, going from reaction to reaction. So what we see here is that reactions, K becomes bigger, reactions become faster when activation energies are small, all right? Or I like to think of it this way. when is it faster to go over a hill? If the hill is big or if the hill is small? When the hill is small, you go over faster, all right? So small activation energies lead to faster reactions. Or the other trend that comes out of this Arrhenius equation is how temperature is involved. What we see, and it follows our instincts, is as a temperature increases, that whole value of K increases as well. R is a constant, so that's not changing. Really, the only things we're going to inspect here are how activation energy and temperature affect our rate constant. Okay, so let's look at a molecular view of reactions and dive deeper into collision theory and why collisions lead to chemical reactions. So let's think about a single collision between two reactants, all right? That collision can have a certain amount of energy related to it. You can smash those particles together, or they can just like graze each other very gracefully. And so only one of those scenarios, a reaction will actually happen, and it's dictated by this energy curve and the activation energy related to that reaction. So here's our reaction. Here's our reactants. Here is our products. In order for this reaction to happen, we got to clear this hill. We got to clear that activation energy. So here are four different scenarios of collisions. This first collision, very low energy. This second one, a little bit higher in energy. The third one, we're smashing them together a little bit harder, a little bit more energy. And then the last one, lots of energy. So only one of these scenarios for a single collision, a reaction will actually happen. And that's this last one. Because for a single collision, we need to be able to clear that hill, that activation energy hill. Versus the other three, when we smash together these particles, there's not enough energy for that collision to lead to an actual chemical reaction. I like to think of a ball, right? If you think of like a ball traveling along this reaction coordinate diagram, you know, you can roll your ball up to this point, and then it's just going to roll back down and stay on the product side. Versus this one, okay, you send the ball up with a little bit more speed. It goes all the way up here, but it still doesn't clear that activation energy. It just rolls back down to the reactant side. Versus the last one, where we roll the ball up the hill, it clears the activation energy, and then it rolls back down to the product side. So only that last one for a single collision actually leads to a chemical reaction, right? Okay, perfect. All right. But here's the thing, when we have gas samples, it's not just a single collision. It's actually a lot of different collisions, because in a gas sample, we have tons and tons of particles. So let me ask you this question again. In a gas sample, are all the particles moving at the same speed? No, they're not. They're all moving at different speeds. So in a gas sample where there's lots of collisions, are all of the collisions going to be the same energy? They're not, because all the particles, they're going at different speeds. So let's inspect a single collision versus a many collision system, which is more pertinent for our cases, because we're always working with, you know, more than one atom here. So in this example, for a single collision, we collide these two particles with this amount of energy for a single collision. Does a reaction happen? No, it doesn't, because you just kind of roll the ball up and then it rolls right back down. So in this case, no, a reaction does not happen. So that is the total energy of that single collision. But see how the language changes a little bit for this many collision system. See, there's tons of particles all bouncing around like crazy idiots in this sample, but they all have different speeds. So how we represent this is instead we say, okay, here's the total average energy of this sample. Some of those particles, they're going to have collision energies that are slightly lower than this average. And then we're going to have some particles that have collision energies that are slightly higher than this average. So notice that this line just tells us the average energy. We have collisions that are above this line and below this line. So in this many collision system, products actually do in fact form because the average total energy is above that potential energy of our products. That you just might have you know, a freak accident where two particles with lots of energy collide in with one another and does actually go over this hill. And so that's the difference between a single collision and a many collision system, is that in this many collision system, some particles collide with more energy and less energy, and just a fraction, a larger fraction or a small fraction in this example will actually clear that hill, because not all collisions have the same energy. It's just how we're representing this is the total average energy. And so what we see here, if we go back to the Maxwell-Boltzmann distribution, what we can see is if this is the minimum amount of energy needed for a reaction to happen, you see at higher temperatures, more of those collisions actually exceed that energy, that minimum energy required. If we were to raise the temperature even more and like the distribution looks like this, we would see, oh yes, in this even higher temperature, an even larger fraction of those collisions lead to chemical reactions. And this is why increasing the temperature leads to faster reactions, because at higher temperatures, more collisions actually result in chemical reactions. And more of those collisions actually overcome that activation energy. Okay, all right, so that's single versus many collisions. Okay, so let's look at this a little bit more and think about, what is the purpose of this activation energy? Why do we have to give this reaction a little bit of energy in order to get to the product side? So the reason that reactions have a activation energy is because we have to produce this unstable complex, this what we call an activated complex, in order to make the product. So if you can think about a collision, when we collide two particles together, for a split moment in time, we create this really unstable substance before it actually becomes a product. And here is an example. If this is my reactant, and the product I want to make just swaps the carbon and nitrogen atoms, in order to do this swap, see how we're like changing nitrogen's there, but now the product, the carbon, is there instead. So there's this intermediate, I don't want to say the word intermediate, there's this activated complex, this really unstable species that's produced before we actually go from reactant to product. And that's this activated species, where we've essentially broken that carbon-nitrogen bond. We've broken it. And so at that point, once we've broken it, see how this bond is broken? This is very unstable. This is very unstable, and it has a very high potential energy. It's very unstable. And so this is the purpose of this activation energy, that we need enough energy to make this activated complex. We need enough energy to actually break this bond before we make our products. And so what we see is that the activated complex is most pertinent at the top of this hill. We can't actually isolate this activated complex. It's very, very unstable, right? So there's the answer there. No, the answer is no. You cannot isolate the activated complex. I like to think of this, reaction coordinate diagram like a ball. If you put a ball at the very, very top of the hill, that ball is not stable there. It's going to roll to either side, all right? So that ball's not going to stay there. It's very unstable. You can't actually isolate that activated complex. It's going to tend to go either to the reactant side or product side. It's not going to stay up there. But what we see is, in order to go from reactants to activated species, we need to give this reaction energy. We have to basically break those bonds required to make that activated species. It requires energy to go up this hill. And then so what we see is that forming that activated complex is going to be much more probable at higher temperatures, because there's more kinetic energy. There's more kinetic energy to get us over that hill. Right? And then we can go to product side. Okay, there we go. Okay, the picture again. And so let's think about this reaction in both the forward direction and the reverse direction. So what we saw from the Arrhenius equation is that typically reactions that have very large activation energies, really tall hills, these are slow reactions. So large activation energies typically mean small k's, or we can say slow reactions. All right? So large activation energy, small k, slow reactions. So based upon that fact, let's look at this reaction and think, what do we think is faster? This reaction going in the forward direction or the reverse direction? Just think about like walking up a hill. right? You're over here and your friend is over here. Who gets over the hill faster? The person going forward, not the person going in reverse. So what we see here is that the forward reaction is much faster than the reverse reaction, and it's because the activation energy for that forward reaction is smaller. It has a smaller, so activation energy in the reverse direction, all right? That's much faster. I'm going to exaggerate this. Much faster going in this direction than it is going in this direction, because the hill is smaller going forward, but it's a lot larger going in the reverse direction. Right, so see, let me actually draw those activation energies. Here is the activation energy in the forward direction, right? So small hill, but then this entire energy is the activation energy going in the reverse direction. So what we see here, it's a lot easier to go forward than it is to go in reverse. So that means if we let this reaction kind of go over time, and we let it go forward and reverse at the same time, what we would see is that products would start to accumulate. Products are favored because it's easier to go forward than it is to go backwards. And this detail will be very important in chemical equilibria that we'll talk about very, very soon. Okay, there we go. Forward products, perfect. All right, so I mentioned that the Arrhenius equation that we introduced, this equation really just tells us trends. I never actually have you calculate anything. And those trends were that reactions go faster when either activation energy is low, so small hill, or when temperature is high. All right, so that equation really just tells us trends. So how can we actually calculate important aspects using the Arrhenius equation? So instead, we will use what we call I like to call the two-point Arrhenius equation. So, or the integrated Arrhenius equation, where we can look at a reaction done at different temperatures. Because what we see is that as we increase the temperature of a reaction, they always go faster. And you'll actually do this in lab. I think it's the CLK lab. You'll do a reaction at like 4 or 5 different temperatures, and you'll be able to extract an activation energy out of it. And how we do that is by integrating the Arrhenius equation. And so what we do is just like what we did with the integrated rate laws, is try to turn this Arrhenius equation into a straight line. And so I've done that for you. I've done the calculus for you, where we take the natural log of everything. So what comes out is that the natural log of K, your rate constant for your reaction at different temperatures, is related to your activation energy. And so you can plot this. So what you see here, and this is exactly what you'll do in lab, is you will plot natural log of your rate constant at different temperatures, but your x-axis isn't just going to be straight up temperature. You're actually going to graph 1 over temperature, so the inverse of temperature. But what comes out is a beautiful straight line for a single reaction. So what we see here is 4 different points make a straight line, and what this slope ends up being is related to your activation energy with a factor of R, your gas law constant, related to it. I'll remind you that that R is 8.314 joule mole Kelvin, and it's because activation energy is an energy term. And so that comes from the Arrhenius equation. You will use this form of the Arrhenius equation, not so much this one. We'll use the integrated form. So looking at a reaction with a bunch of different rate constants at different temperatures. But here's the thing. On exams, it's very difficult for us to ask you to graph things. So instead, we will give you a 2-point version of the integrated Arrhenius equation, because here's the thing. 2 points will always make a line, right? That we just need 2 points to figure out what that slope is. So here is that integrated form, where we essentially just take that integrated Arrhenius equation for 2 separate points and manipulate it so a nice equation comes out. So what we see is, okay, as long as you measure the rate constant at 2 different temperatures, so you're going to do the reaction at least 2 times, you can use this last squared equation. So here you see, and just be very careful of the variables, that your rate constant at the first temperature over the rate constant at your second temperature, so take that ratio, take the natural log, is equal to the activation energy for that reaction over R. This is the same energy term of R, so use the 8.314 version, times the inverse of your second temperature minus the inverse of your first temperature. So do note where K1 and T1 show up and where K2 and T2 show up. So K2 is the reaction rate constant at the second temperature. K1 is your rate constant at the first temperature. So just be very careful of where you place those numbers because you're going to actually measure 2 rate constants and 2 temperatures, right? So what comes out of this equation, what we see is that increasing your reaction more usually leads to a larger increase in your rate constant. That makes sense. Heating it up more increases the speed more. So that's one kind of trend that comes out of the equation. And then another kind of smaller, kind of more difficult trend to kind of pull out of this equation is that, okay, your activation energy for your reaction also dictates how much your reaction speeds up. And so here's a tip. The larger your activation energy for your reaction, the larger the effect that temperature will have on your rate constants. So what I like to say is that reactions with a large activation energy are more sensitive to temperature changes. I like to think of it this way. If you have a reaction with a large activation energy, is that reaction going fast or slow? Slow. Okay, so the reaction's already going slow. So if you give a slow reaction more temperature, more energy, it's going to take that energy and increase its reaction rate a lot more. Versus if you have a reaction with a really small activation energy, that reaction is already going what? Fast. So if the reaction's already going fast and you give that reaction more temperature, more energy, it's going to go faster, but not as much. Not as much. And this is the analogy I like to use, okay? So pretend you give me $1,000, all right? Think about what you could do, how $1,000 would change your life right now. Would it change it considerably if you gained $1,000? Yeah, you could go out, buy that new phone, buy the whatever you need, buy a new laptop, it would change your life, okay? Now give $1,000 to Jeff Bezos. Okay, Jeff Bezos, he's worth like $5 billion. If you give $1,000 to Jeff Bezos, does he become richer? Technically, like on paper, does he become richer if you give him $1,000? Yes, but will it change his life? No, it won't. It's a drop in the bucket because he's already going fast. You give him more temperature. Yes, he's a little richer, but there's not much of an effect. Versus us, if you give us $1,000, right? Our activation energy is already really high. We're already going very slow in life. It's going to make a bigger difference, all right? So there's my analogy, all right? That reactions that are already going slow, they get more out of, they're more sensitive to temperature changes. So let's put that together, okay? Here are 2 reactions. The first one is an exothermic reaction, all right? So A to B, you see there's an overall loss of energy. This reaction releases energy. But going for reaction 2, going from reactants to products, there's an overall increase in energy. So this is endothermic. So delta H is positive here, delta H is negative here. So in which scenario? Let's just go in the forward direction. Which reaction has the larger activation energy? Reaction 1 or 2? 2. Pretend that these are to scale, all right? So what we see here is that there is your activation energy for the second reaction, bigger hill, versus the first reaction, there's its activation energy, smaller hill, okay? So based upon those activation energies, which reaction is going faster? Reaction 1 or 2? 1, because small hill, you go over it fast. Okay, perfect. So what happens when you heat up both of these reactions? Will reaction 1 go faster if you heat it up? Yes. Will reaction 2 get faster if you heat it up? Yes, they will both go faster. But what's the difference? One of them gets faster more. And which one is that? Reaction 2 actually increases more. So I think the correct answer is C. Yeah? Because C, reaction 2, is already going slower than reaction 1. So it's going to do more with that increase in temperature than reaction 1. Both of them get faster. Both of them become richer if you give them $1,000. But reaction 2, because it's already going slow, gets more out of it. So I think the correct answer is C, all right? So do not say that both reactions go faster the same amount. That's not true. Since they have different activation energies, they will go up in different amounts dictated by this equation, all right? And it's all based upon the magnitude of that activation energy, all right? And you could test it out too. You could use this equation, inspect 2 different temperatures with different activation energies, and you'll see a reaction with a larger activation energy has a larger change in that first and second rate at 2 different temperatures. Okay, so there's the concepts behind calculating things. So let's do the last mathematical one. All right, I showed you a lot of different equations in the past, 40 slides in this chapter. So let's make sure that we use the right one. We're talking about activation energy. This information I'm giving you here, I say, okay, you study a reaction at 2 different temperatures and you collect the rate constants. You observe that the rate doubles when you increase the temperature from 200 degrees Celsius, so I think this is 293 Kelvin, to 60 degrees Celsius, so this is, I think, 333 Kelvin. All right, and so I want you to estimate what is the activation energy in kilojoules per mole. So if you look back at all of our equations I've showed you, a lot of them have activation energy, a lot of them have rate constant. We want to make sure we use the right one. So this first equation, it has activation energy in it, but we don't actually want to use this because we need an equation that has 2 temperatures and 2 rate constants. So we don't want to use that first one. That's not going to help us. This second equation has rate constant in it, but there's no activation energy, there's no temperature term here. We don't want to use this. This equation is actually the, what is this? This is the first order integrated rate law, all right? That's just comparing concentrations. I don't want that. I need something that tells me a relationship between rate constants and temperature. And so the equation we actually want to use is this one because it has 2 temperatures, 2 rate constants, so it's just plug and chug. So the last one we don't want to use because this is would be solely for graphing, because you could graph this y equals mx plus b. But since this is just 2 points, it's fine enough to just use the 2-point version of the Arrhenius equation here. Okay, so it's just plug and chug, but we just got to be very careful with our units. So I tell you that our first temperature is 293 Kelvin, and then our second temperature is 333 Kelvin. But technically, I didn't give you any rate constants, right? I didn't give you a rate constant. I didn't give you how fast this reaction goes. So we have to infer it. I do tell you that this rate doubles. The reaction doubles in speed going from temperature 1 to 2. So let's just make up numbers, all right? So let's just say the rate constant for the first temperature, I'm going to pick an easy number. What should I pick? 1. Yes, let's just say it's 1. So based upon the information given in this question, what should the rate constant K2 be? It should be 2, yes, right? We just need the ratio. Doesn't actually matter what the numbers are, okay? All right, and those would have units. They could be like molarity per second. It really doesn't matter because in the end, we just take the ratio anyway. So now we have all the numbers we need to calculate activation energy. We have K1, K2, T2, T1, R is a constant, so we just solve for activation energy. So let's go ahead and do that and be very careful about where we place those numbers. So this is natural log of K1 over K2, so 1/2. Natural log of 1/2 equals, if I actually gave you the rate constants, then put in those numbers, but I didn't. EA, that's what we're solving for. R, we're going to use the energy version of R, so 8.314 joule mole Kelvin. And so I already converted those Celsiuses into Kelvins, and we know they should be in Kelvin because we're using R, that gas law constant. So we're going to take the inverse of T2. So this is 333 to the negative 1. So take the inverse of that. Minus 293 to the negative 1. All right. I think I wrote down these answers. Okay, so now you see there's just one variable, and we just need to isolate it. So if I do the temperatures there, if I take 333 to the negative 1 to 293 to the negative 1, what comes out is negative 4.099 times 10 to the negative 4. All right. So I'm going to multiply by that denominator also. And so I get, let's clean this up. So natural log of 1/2 is negative 0.693 equals activation energy. So if I multiply all of these things together into one term to isolate that activation energy, I get something like negative 4.93 times 10 to the negative 5. So I'm going to take this number and divide by activation energy, 8.314. All right, and so what we get is that activation energy, if you divide both sides by negative 4.93 times 10 to the negative 5, you get a number like 1400.053. All right, and so we just need to get the unit here. Activation energy, it's going to be in an energy term. And so that energy term is going to come out to be joules per mole. And the reason it comes out to joules per mole is because of the unit of R, our gas law constant. It's a joule per mole Kelvin. We're multiplying by some temperatures, so the Kelvin falls out. So the unit here is joules per mole. And so that's a really big number. I don't really like it, so let's convert that to kilojoules instead. And so we get, yes, that activation energy for this reaction is something like 14.1 kilojoules per mole. All right, so there is the work for the 2-point Arrhenius equation, where I give you 2 temperatures, 2 rate constants, and you determine what that activation energy is there. And so just note that it's K1 over K2, and then you're subtracting T2, the inverse of T2 minus the inverse of T1. You are given this equation, but just make sure that you're putting things in the right spots. All right, so that's how temperature is related to rate laws. Temperature affects the value of K, your rate constant. So these Ks that we were inspecting, this is the same K from those rate laws that we looked at earlier. Okay, so let's move on to the last part of the chapter. So reaction mechanisms. Oh, this is actually where midterm 2 material starts. So this last slide will be on midterm 1. I can guarantee you, you will have to use the integrated rate law once, or not, sorry, the integrated Arrhenius equation at least once on the midterm. So that is where midterm 1 material ends. And so what we're going to look at now is midterm 2 material. We got to keep going. And we'll look at the last way to get a rate law, and that is reaction mechanisms. Okay. Okay, great. All right, reaction mechanisms. So what we're going to look at here is I already showed you that some reactions can happen in more than one step, and we'll look at that in mechanisms. Okay, so this is the third way to get a rate law. So I mentioned before that, okay, a reaction doesn't necessarily have to go from reactants to products in one step. It can be multiple steps. It's kind of like building a bike, all right? If you build a bike, usually there's more than one step involved. If you received instructions for building a bike and it just said build bike, you would be really mad, all right? Because that's not helpful. You want to think about all the individual steps, all right? So when you get instructions to build a bike, usually there's many steps, let's say a dozen steps to build it, put together the wheel, tighten the bolts, whatever. Oftentimes one of those steps take longer than the other steps. We call that a rate determining step. It's the longest step. The slowest step is typically what dictates your rate law in your reaction. So here's an example. This reaction occurs in 2 separate steps. The reason I know it occurs in 2 separate steps is there's 2 activation energies. If you think about, walking up this hill, you have to get over the first hill first. That's going to be quite hard. But then you have to go up over a second hill, right? So this reaction is happening in 2 steps. Based upon the activation energies, can you tell me which is the slowest step? The first step or the second step? The first, yeah, because that one's the biggest hill, yeah, and that's going to be important here in a little bit. So here's an example of what this reaction would look like. So for a 2-step mechanism, for a reaction where an A atom combines with 2 B atoms gives you this molecule, BAB, so 1 molecule here. It could happen in 2 steps where A and B combine to make AB, and then AB combines with that last B atom to give you your product. So here you're seeing, oh, the B's are just adding on one at a time, but each of those are its own step, each of them with its own rate constant. And so what we see here in this 2-step mechanism, AB, this particle that's produced in that first step, it cancels out. So it doesn't show up in this overall reaction. So notice in the overall reaction, we just take what's left over, an A atom, 2 B atoms to yield a BAB atom. That's our overall reaction. But what happens is AB gets canceled out. It doesn't actually show up in the reaction, the overall reaction. So we call that an intermediate because it's produced and then consumed in the next step. It doesn't actually show up in the reaction. And we'll see that here in a little bit. All right. So here's the thing. A mechanism is just a proposed idea. We can't actually see atoms. Okay, we can't see them. We can't actually see the individual collisions. We can only just imagine what it looks like. So these mechanisms are just a proposed idea. But here's the thing. We already looked at 2 other ways to get rate laws. So we need to make sure if we propose a mechanism, like a made-up idea of what's happening, we need to make sure that that mechanism matches what we observe via the other ways we get a rate law. Like if we know the rate law for a reaction and we propose a mechanism, we need to make sure the mechanism matches the rate law that we observe. And that's the big idea here. So we're going to actually put it all together, all 3 of those ways to get rate laws. They're all related to one another. They have to match one another. If you get that, oh, a reaction is first order, you need to make sure your mechanism also shows that it's first order. Okay, so how do we get mechanisms? Mechanisms is my favorite way to get a rate law because it's like a little puzzle, right? So for rate laws for mechanisms, we are assuming, we're making an assumption that each of the individual steps in a mechanism are what we call elementary reactions, meaning that it's just a single collision. Okay, so if your reaction, your elementary step is a single collision, then now you are allowed to just take the stoichiometry from your step and turn that into the exponents in your rate law. You are now allowed to do that for elementary steps in reaction mechanisms. So here are some examples. If these are all elementary reactions, so remember in rate laws, we only took the reactants and then put those into the rate law. Those are the only things that matter. So here are some examples. If A goes to make products, and this is an elementary step, this has a rate law of just A to the first power. If you have an elementary step where 2 A atoms collide with one another to give product, if this is an elementary step, it is A squared, right? So now you are allowed to take the coefficients and turn them into exponents, but only for elementary steps. In all the other the ways that we got rate laws, like the method of initial rates, the, what was the other one? Integrated rate laws, those ones we're assuming were not elementary steps, so we actually have to use data to figure it out. But here with mechanisms, we can just take the reactants and their coefficients and turn them into exponents. So here's another example. If 3 A atoms combine all at the same time, yes, it is A cubed, as long as it's an elementary reaction. But I will point out that these termomolecular reactions are very uncommon. Because if you just think about it like in a system, the likelihood of two particles colliding is very high. That's what a like normal collision is. But the probability of three particles all colliding at the same time in the same spot, like in space, is very unlikely. So termomolecular, so three atoms involved in a single collision, is very uncommon. All right, so what we're usually going to see is unimolecular and bimolecular steps. Okay, all right. Okay, so let's keep going. All right, so here is a two-step mechanism. So from these steps, we should be able to get an overall reaction. All right, this is where we kind of just like do Hess's law and we cancel out things that show up on the reactants and the product side. We can look at each individual step to get the molecularity, and then we can get the rate law for each of those individual steps. So let's get that overall reaction. So what we want to do here is just add these two reactions up, just like Hess's law, and make sure that we cancel things out that show up on both the reactants and product side. So if we look closely here, in that first step, we make HI, and it's consumed in the next step. So that gets canceled out in the overall reaction. Is there anything else I can cancel? No, that looks like it's it. So if you look and see what's left over, we see, okay, we have an H2 particle, and it's combining total with two ICl particles. And then our products is an I2 molecule, and we get two HCl's out. So our overall reaction is H2, everything's in the gas phase, so I'm just going to drop it. H2 plus we are combining two ICLs, arrow products. We get an I2 molecule and then two HCl's. Perfect. So that's our overall reaction. So we see that HI got canceled because it was made in the first step but then consumed in the next step, just like in Hess's law, right? So that's our overall reaction. It adds up. All those steps have to add up to the overall reaction. If you check the atoms, yes, we are atom balanced. Okay, so the molecularity of each elementary reaction. So we're going to look at each step individually. So I'm just going to erase all this work I did. So we're going to look at each step individually. We see that the first reaction, we're combining two atoms or two particles. So this is a bimolecular step because we're just colliding two particles. And also the second step is also bimolecular because we're combining two atoms or two particles, I guess. All right, so both of those are bimolecular. And so we should be able to get the rate law for both of those, and they should be both second order reactions because they're both bimolecular. So simply because these are elementary reactions, we can just take the stoichiometry and turn them into coefficients. We don't need to, look at experimental data. We are just looking at the stoichiometry. So for step one, the rate of that first step is equal to the rate constant for that first step. I don't know what it is, so I'm just going to call it K1 times the concentration of H2 times the concentration of ICl. Right? So simply we're just taking those reactants. And then the rate law for the second step, same idea, but this time it's the rate constant for that second step. Again, I don't know what it is, so I'm just going to call it K2, where the rate law is dependent on how much HI is present and how much ICl is present. All right, and so the last question here, identify any intermediates in this reaction. So HI is an intermediate because it got canceled when we got the overall reaction. And so this will be an issue in a little bit because when you look at the rate laws for the individual step, the first step, the components of that rate law is dependent on concentrations of reactants that we put in our reaction. But what will be a problem in a little bit is the rate law for the second step we see is actually dependent on the concentration of an intermediate. And that's going to be an issue coming up in a couple slides. Okay, so HI is an intermediate because it got canceled out in the reaction when we got that overall reaction. Okay, so now let's get the rate law for the entire reaction. We just looked at the individual steps, so now let's put it all together in an exam-like question. Okay, so here's the big idea for a multi-step mechanism, just like building a bike. The rate at which you produce bikes is dependent on the slowest step of the building the bike process. So we're going to use that same analogy here. Whichever step for a multi-step mechanism is the slowest is what determines the rate law. And so we call that the rate determining step. The slow step determines your rate law. The slow step is usually a elementary reaction, so we can simply just take the stoichiometry and the reactants, bam, there's your rate law, right? So there are two types of mechanisms that we'll study. The first one is the easy one. It's when the first step is the slow step. That's a very easy mechanism to solve. Then the second one we'll look at, it's a little bit harder, but it's not that bad, is when the second step is the slow step. And we'll look at how to solve the rate law for one of those, okay? And so here's an analogy in the book. It's like if you are on a highway and there's two toll booths. Let's say the first toll booth is like really slow and there's a buildup there. If you were to watch how cars would move through this highway, it's this first toll booth is what's dictating how fast cars can go through. If, let's say, toll booth A is like closed, like, you know, very, very slow, but toll booth B is very, very fast, once a car goes through A, it's just going to stroll through the second toll booth. So this first step is what determines the overall flow of traffic, versus if the second step is the slow step, let's say the second toll booth is slow, everyone blazes through the first toll booth, it's this second step is what dictates the overall flow of traffic. And so that's the analogy here. All right, so keep that in mind. It's the slowest step determines your rate law. So let's go back to this example. We already said that the first step is the slow step. You can tell because this first step has the highest activation energy. So if I tell you that the first step of this mechanism is the slow step, and I tell you that that step is this elementary reaction where A and B combine to make AB, what is the rate law for this reaction? All you have to do is take the slow step and write the rate law. The rate for that slow step is equal to K1 times the concentration of A times the concentration of B. And that's it. That is your rate law. So we just determined via this mechanism that it's first order with respect to A, first order with respect to B, because that is what's present in that first step. And notice that these coefficients or these exponents, it differs from the overall reaction. And it's because the rate law is based upon the mechanism, not the overall reaction. The reaction is a multi-step mechanism, but these individual steps are elementary reactions, so we can go ahead and just turn stoichiometry into coefficients. So that's it. So for any slow step mechanism where the first one's the slow step, you just take the reactants and shove them into your rate law, just like that, right? And I mentioned before that AB is an intermediate and cannot show up in our rate law coming up. It'll be an issue for the next kind of mechanism. Okay, so there's our rate law when the first step is the slow step. So let's do another one. Here's another reaction. Here's my proposed mechanism. And I tell you that the first step is the slow step. So what is the rate law for the rate limiting step? So this is the slow step. I just want you to tell me what's that rate law for the slow step. So this is step 1. So step 1 has a rate law of rate. I'm going to multiply this by K1, so the rate constant for the first step, which is different from the rate constant of the second step. And I'm just going to take the concentrations of your reactants. So in the first step, we have NO2, but it is squared. So this is another bimolecular reaction, but it's 2 NO2 particles. All right, so that's the rate law for the slow step. So what is the rate law for the entire reaction? It's just the same thing all over again. Yes, because the slow step is the rate determining step for the entire reaction. So yes, it is the same thing. The rate equals K1 times NO2. Okay, so what we see here is that this reaction, its overall speed is not dependent on the second step. So you can pretend like, okay, let's pretend we're building a bike. All right, like we work at a bike shop and we want to output a bunch of bikes. The first step of building a bike is, let's say, is really slow. Like it's, you know, putting together the wheels and all of that's really slow. Let's say the last step of our bike shop is slapping a bow on the bike. That's really fast, right? So is that last step, slapping a bow on the bike, is that going to affect the overall rate of the whole reaction we see? No, it's not. It's all of the slow steps leading up to it. So what we're seeing here is that first step determines the overall speed of this reaction, but that second step, because it's really fast, does not, right? We're assuming it happens basically instantly. All right, so let's put it all together. So based upon the rate law that we just got, and look at the reaction that's happening. We're combining NO2 and carbon monoxide and getting products. What if I doubled the amount of carbon monoxide in my reaction? How would the reaction rate change? Will it change? It won't. No, because just like before, CO isn't in our rate law. So CO is concentration is not going to actually affect the overall rate law because it does, or the reaction rate, because it's not inside the rate law. Just like we said before, we basically determined that CO is 0th order, right? And the reason is because it shows up in the fast second step. So its concentration doesn't really matter. It just has to be present in order for that second step to happen because it's so fast. Okay, let's do one more. All right, so here is a two-step decomposition of hydrogen peroxide. It follows a two-step mechanism. Slow step is the first step again. Wahoo. Let's get the overall chemical reaction. All right, so we're going to add these two reactions up. It's a little bit more complicated than our last one, so we got to be careful. What things cancel out of this reaction? What things show up on both the reactants and product side? The first one, IO minus, that cancels out. Yeah? Anything else cancel out? I minus, yep, that cancels out too. But notice how it cancels out different, all right? Look at the first one I canceled, IO minus. Think about how it's involved in the reaction. IO minus, it's made in the first step, and then it's consumed in the second step. IO minus is an intermediate. But notice how I minus gets canceled out of the reaction. See how it's a little bit different? I minus is consumed in the first step, but look, it's produced at the very end. See how it's a little bit different? I minus is not an intermediate. I minus is actually a catalyst, okay? Because I have to add it to the reaction, but it gets made again at the end, so I get it back, but I still have to add it at the beginning. And the explanation between intermediate and catalyst are at the bottom here. I like to think, because here's the thing, intermediates and catalysts, they're both canceled out of the reaction just a little bit differently. Intermediates, I like to say they're made and then consumed. They're a product and then a reactant, but a catalyst is consumed and then produced at the end. So it's a reactant then a product, right? So they get canceled out a little bit differently. All right, but everything there gets canceled, so then we get the chemical reaction. H2O2, aqueous, oh, there's two of them. There's two of them, 1, 2. And what do we make? We make 2 waters and an oxygen, perfect. So boom, 2 waters, liquids, and an oxygen, perfect. And so we see that iodine business all gets canceled out either through an intermediate or a catalyst. Okay, what is the rate law for this overall process? So just like before, we're going to take the rate determining step, which is the first step. It's the slow step. And we're just going to say rate equals K1, the rate constant for the first slow reaction, H2O2, times how much catalyst you have. So in this case, a catalyst does show up in the rate law, and that's okay. That's okay. It's okay because you have to add a catalyst to a reaction if the reaction's catalyzed. What you can't add are intermediates, so I could not have IO minus in this rate law. Okay, let's answer this question. What's an intermediate? So IO minus is an intermediate, and we said I minus is a catalyst. Okay, perfect. All right, so based upon that, let's look at this reaction mechanism. Tell me, based upon this two-step mechanism, where on this reaction coordinate is IO minus concentration the largest? So ask yourself, what is IO minus? If you look at this reaction, it's produced in the first step and then consumed in the second step, all right? It's an intermediate. So where on this reaction coordinate diagram will its concentration be the greatest? Probably right after it's produced, right? So what spot is that? C, yes, right here. So you can think, all right, this is your first step. There is your second step, all right? So IO minus concentration, the intermediate is going to be highest in concentration between those two steps. So let me ask you this. Remember we talked about activated complexes? That's like spots B and D. Can you isolate things in spots B and D? Nope, but could you, in theory, isolate an intermediate? Yes, because if you put a ball there, will that ball stay there? Yes, it will. So you could, in theory, isolate an intermediate if you wanted to, because it sticks around long enough that you can grab it. Okay. Cool. Oh, yeah, it says right there. Activated complexes can't be isolated, intermediates can. Okay. So let's put it together. Remember, mechanisms have to match your rate laws that we got previously in this chapter, right? We talked about the other two ways to get rate laws, the method of initial rates or integrated rate laws. So let me tell you, let's pretend we have this reaction, two A's plus a B, but I tell you that the rate law is K, rate law is K, rate constant times B concentration. So this reaction is first order with respect to B. So like we did method of initial rates, and that's what we got, all right? So which mechanism is consistent with that? The first one or the second one? The second one, yes, because both of these are the slow first step, so they're the easy ones, right? So here, for this first mechanism, your rate law is K times A times B. But the second one, rate, again, because the slow step's the first step, is equal to K times B. So here, yes, the second mechanism is consistent with the rate law that was given. All right. But both of these, if you check your work, both of these, if you cancel out your stuff and get the overall reaction, both of them add up to the overall reaction, but only one of the mechanisms is right because it has to be consistent with the rate law. The first one, M cancels out, so you get 2A plus B gives you C and D. But in the second one, M cancels, and I think N cancels, so you get B plus 2A's gives you C and D. Both of them add up to the overall, but only one of them matches based upon that mechanism and the rate law that was given. Okay, so yes, there we go. All right, so we did the first one, the first kind of mechanism, which was easy. It's when the first step is the slow step. And again, if the first step is slow and it's an elementary reaction, we simply have to just take those the stoichiometry, turn it into coefficients. So the harder one is when the second step is the slow step. So you have a fast step that happens, and then the second step is slow. So what we're going to say is for like a two-step mechanism, we're going to say that first step is fast and it's an equilibrium. So what that means is that this reaction, this first fast step, goes back and forth really, really quickly. Goes back and forth really, really quickly. And that second step is the slow step. So this is the process, the strategy. The strategy is actually this exact same, okay? Where the slow step is the rate determining step, the slow step determines your rate law. So if the second step is the slow step, we simply have to write the rate law for that second step, right? So let's do that. Second step, slow step. So that means your rate is equal to K2, so the rate constant for the second step, times your concentration of B times your concentration of M. So if we look at this reaction, the overall reaction is you're combining A and B to give C and D. So we have a problem because our rate law right now, it has B present, but it also has M present. Is M in our overall reaction. Can we actually add M to our reaction? No, it's an intermediate. That's not allowed. We can't have an intermediate in our rate law because we never added it to the reaction. So this is the trick to get rid of the intermediate. We're going to use the fast step to get rid of it. Okay? And we're going to utilize the idea that the first step is a fast equilibrium step. So what we're going to do is we're going to use the fast first step, say, since this reaction goes back and forth really, really quickly, we're going to say, since this is at equilibrium, that the forward rate of this reaction, the first one, is equal to the reverse rate of this reaction. All right, so that's what an equilibrium is. We'll talk about that in a little bit. All right, so what we're going to do is write the rate law for the forward direction of the fast step and set it equal to the rate law of the reverse direction. So simply what we do, the forward rate law is K1 times A concentration squared. And that is equal to the rate constant for the reverse step. So K negative 1, so the rate constant for the reverse direction, times the concentration of M. So what I essentially did was set the reactants and the reactants multiplied by one another equal to the products multiplied by one another, right? So this is useful to us because now we can rearrange this and get an expression that has M in it. So if I rearrange this and isolate M, I get that M is equal to a bunch of K's. So K1 over K negative 1 times A squared. That's what I got. And that's really useful to us because now we have an expression where we relate M to A. And so now simply we just replace that M with the M that came from the fast step. So now we can replace that M and get that rate for this reaction. And I'll combine these K's together. So it's K1 times K2 over K negative 1 times B concentration times A squared concentration. All right. But here's the thing. I have a bunch of K's, rate constants for the individual steps here. You will never actually observe those individually. So an easier way is just to combine all the K's, and we can instead just say that this reaction has an overall K, but it is first order with respect to B and second order with respect to A. And that's really what's important here, right? So the idea here is that our slow second step, we write the rate law, but usually there's an intermediate that we have to get rid of, and we just utilize the first step, the fast first step, to get rid of it, all right? So it's not that bad. It's the harder of the two, but it's really not that bad. All right, so let's put it all together. Okay, remember, there's two types of mechanisms. The first one is slow first step. We already did those. Those ones are easy, straightforward. Sorry, I shouldn't say easy. They're straightforward. So this, here's 4 different mechanisms. Let's get the rate laws for all of them. So I already did the first ones for us because they're the slow first step. So here, this first one, the slow step is the first step. So this rate law is first order with respect to A and B. You just ignore the second step. The second mechanism here also has a slow first step. So this reaction is just first order with respect to B, but 0th order with respect to A. We already did those ones. So let's do the harder ones here where, okay, here in the third mechanism, the second step is the slow step. So we use the exact same process we did before where, okay, slow step, we take the rate law from the slow step. So rate is K, I'll call it K2 because it's the second step, times A concentration times M concentration. Am I done? Nope. What do I have to do? Get rid of M. Yep, I'll get rid of M by using the fast first step. So that M is not allowed. Okay, so I'm going to use that fast first step, and I'm going to say K1 times A times B equals K negative 1 times M So we see that M concentration is proportional to the product of A times B. So if you rearrange things, you get that M concentration is equal to K1 over K negative 1 A times B. I know I'm putting all the K's there at the end. They're just the K's are all going to combine to just 1 K. So you really could just ignore all those little K's. All right, so what's important here is that M concentration is proportional to A times B, and then we will replace that M with what we just got from the fast step. So we see that for this third reaction, the overall rate law is K, I'm just going to call it K overall, times A concentration squared times B concentration, because we're combining the A that was originally in that second step, and we're combining another A times B. Beautiful. All right, and then we'll do the last one here. Okay, again, second step is the slow step. So here, our rate is equal to K2 M concentration times A concentration. We can't stop there because we cannot include M because it's not part of the reaction. It's an intermediate. So we're going to, again, use the fast step to get rid of M. M is equivalent to the concentration of what? B. Yeah, so just that B is going to replace it. But I'll do the whole work for it anyway. So the fast step, again, you set the reactant rate laws into the forward rate law equal to the reverse rate law. So we say that K1 times B equals K negative 1 times M. And so, yeah, we see M concentration is proportional to B concentration. So when we combine everything, I'm just going to combine the K's together. Rate equals K overall times, what is this? A concentration times B concentration. Great. And that's how we do mechanisms, right? It's not that bad. It's one of my favorite ones because it's a cute little puzzle. But so the interesting about all four of these reactions, it wasn't just like 4 random mechanisms. All of them, if you look at all of the steps and add them up, all of them add up to the same overall reaction. All of them add up to 2A plus B gives you CD. But look, almost all of these mechanisms yield different rate laws, and it depends on what the individual steps are in the mechanism, and it depends on which one's the slow step, right? So here you might be scared sitting there, oh my gosh, do I have to figure out a mechanism on an exam? No, you don't. No, you don't. So what I have starred here is that you will never be asked to propose a mechanism. Instead, what I have you do is I give you a mechanism and I ask you, is this mechanism consistent with this rate law or something, all right? So never am I gonna have you make up a mechanism on the spot. I usually give you the mechanism, but you need to figure out what is the rate law related to that mechanism, all right? And usually I give you what the slow step is, okay? So just an idea here with mechanisms. Again, I'll remind you that mechanisms are just proposed ideas. It's what we imagine happening on a particle level. We can't actually prove mechanisms right. So if we want to use correct scientific language, what we want to say is that this mechanism is consistent with the data that we see. And that's how that's like the PC term, I guess, of saying it's like the like corporate world. Like we don't want to say, oh yeah, I'm right, because that has like implications with it, because we can't actually prove we're right since we can't see atoms. So instead we just say this mechanism is consistent with the experimental data. That's our corporate language that we use, all right? Because we can't prove a mechanism right, but we can absolutely prove a mechanism wrong. As long as we find experimental data that doesn't fit the mechanism, then we can prove it wrong. Very difficult to prove one right. So we just say it's consistent. So here are some examples of like exam type questions where I give you a mechanism and I give you experimental data and I ask you, are they consistent with one another, right? So we're putting it together with ideas with mechanisms and from chapter earlier in the chapter. So let's look at this proposed mechanism. I tell you that the first step is the slow step. So let's just go ahead and write that rate law. So the rate law for this mechanism is K1, first order with respect to NO2, and first order with respect to F2. We can just ignore the rest. So from the mechanism, we just got that it's first order with respect to both of those reactants. So let's remember this experimental data. What do we do with this data? We look and see how do the experimental concentrations change and how does that affect the observed overall rate. So we did this on Wednesday where we look at this experimental data. This is the method of initial rates. Remember, all of this is related to one another. We're always getting the rate law. So from this experimental data, we see that NO2 stays constant in trials 1 and 2. And F2 concentration does what? Triples. And then what happens to the initial rate? Also triples. So what does that tell me about the order of F2? It is first order. Great. So we have the order of one of the reactants. So now let's look at the other reactant. What 2 trials do I want to focus on? Trials 1 and 3. Because what's special about trials 1 and 3 is that F2 stays constant, but NO2 doubles, and then what happens to the initial rate? It also doubles. So that means NO2 is what order? Also first order. So what does that tell us? Does it prove the mechanism is correct? Not necessarily. That's not the right words we want to use. What we want to say is that this experimental data is consistent with the proposed mechanism. Both, all right? We just got that through the method of initial rates, both reactants are first order and it's overall second order. And from the mechanism we got that, oh yeah, both of them it's first order. We want them to match, and that's what we got. So we say that the mechanism is consistent with the data. Okay, let's do another one. Okay, here's our proposed mechanism. There's the overall reaction. So let's get that rate law. Again, first step is the slow step because I want to make it easy. So our rate law is rate equals, it looks like it's the same one, K times NO2 concentration, F2 concentration. So first order with each. All right, so that's my mechanism. And then you go to lab, you collect some concentration data, and you get straight lines with these graphs. So what do these graphs mean? The first graph means NO2 concentration is what order? Notice the y-axis, it's a straight line when it's graphed natural log. So what does this mean? That NO2 is what order in the rate law? First order. Natural logs are first order. But what about the second graph? It's second order. Yeah, this one, because it's graphed 1 over, this experimental data is saying, oh, F2 is actually second order. So do these pieces of information match one another? Is this the correct mechanism, or is this mechanism consistent with the data? It's not. Yeah, so this one is not consistent because F2 is second order, right? Okay, one more here. This one's a little bit different. So here I have your proposed mechanism, slow step, first step, fast step, second step. There's the overall reaction. Is this coordinate diagram consistent with this mechanism? What are we looking at? We're looking at the activation energies. I'm telling you that the first step is the slow step. So if that first step is the slow step, it has to have a small rate constant. Rate constant is inversely proportional to activation energy. Larger hills, slower reactions. So we do in fact see, yes, this first step is going to be slow. It's going to have a small k because the activation energy is so big. That first step, if this was like some, trip or some race you were doing, that first hill is going to take a long time to finish versus that second hill is going to be a lot faster. It's going to be a lot faster. It's going to have a larger rate constant because you have a small activation energy. So yes, this is consistent this reaction coordinate diagram is consistent with that mechanism. All right, so those are the 3 ways to get a rate law. So we did method of initial rates, we did integrated rate laws, we did mechanisms. Which one do you like the most? This one? Yeah, this is fun. Yeah, no math involved. Yeah, so I like mechanisms, they're cute. Okay, so those are our 3 ways, but here's the thing, they all have to match one another, right? In all of them, we're getting a rate law, so for a single reaction, we should be able to see them all match as long as it's correct. Okay, so, last part of the chapter is catalysis. I want to go through this really, really fast, and I'm going to tell you there's only going to be one question on catalysts on the exam, and I'll point out what it is. So I mentioned, all right, how do we make reactions go faster? All right, we have a rate law, like rate equals rate constant times concentrations of reactants, right? If I want this number to be bigger, the rate to go faster, I can either increase the concentration of reactants or I can increase the value of the rate constant. So we already talked about this. Increasing concentrations, that was like method of initial rates. That's how we make reactions go faster to different degrees depending on what the exponent is, what the order is. How can we change our rate constant? We can increase the temperature, right? That's one way we can increase rate constant. We looked at that with the Arrhenius equation, but we also saw that decreasing the activation energy also increases K. All right, so we'll talk about how we do that when we do that using catalysts. All right, so this is what you need to get out of these slides. That catalysts, they make reactions go faster because they lower your activation energy for your reaction, and in turn, they raise the rate constant. All right, but here's the thing. When you add a catalyst to a reaction, you actually mess up the mechanism. You actually produce a new mechanism, a new pathway for that reaction to occur. There's 2 types of catalysts. A catalyst that's homogeneous in nature is usually in the same phase as your entire reaction. So this could be like all gases or like all aqueuses. Everything's like aqueous, like dissolved in water. That's a homogeneous catalyst where everything's in the same phase. While heterogeneous catalysts, they're typically in a different phase. So an example would be like a solid catalyst that's interacting with like gases or things that are aqueous. Platinum is a common heterogeneous catalyst. So how a catalyst works is it lowers your overall activation energy for a reaction. It gives a new reaction pathway. And what we saw is when EA, when activation energy lowers, K increases. That K is the same K in our rate law, and that's why reactions go faster, all right? Remember when we looked at catalysts and how they cancel out in a reaction in multiple steps? You have to add it as a reactant, but it's produced as a product at the end, but it gets canceled out in the overall reaction. All right, so those are catalysts. Okay, so here's an example of what I mean by an alternate pathway, right? So when we think about an uncatalyzed reaction, all right, let's think about the reaction, the decomposition of hydrogen peroxide. You can buy this at Target, right? So what we see here is that this like first aid, item, its decomposition, when we use it, we're actually utilizing the decomposition of hydrogen peroxide. Hydrogen peroxide decomposes into just plain water, but oxygen. All right, oxygen gas. And so we see here is that in the course of this reaction, oxygen gas is generated. So when we buy hydrogen peroxide at the store, has this reaction happened yet? It has not, because if it did, what would these bottles look like? Big and puffy, right? If they're big, puffy, and exploding, then that means the reaction has already happened. But when you go to the store, they're just still the liquid, so the reaction hasn't happened. Okay, but when we use the product and we want the reaction to happen, really what our blood is doing is being a catalyst for that decomposition reaction to happen. I don't know if you've ever put hydrogen peroxide on a wound, but when you do, it bubbles up. And that's what's happening. The reaction's happening because you're giving it an alternate pathway. So when you have the uncatalyzed reaction, it's just one big activation energy. Very difficult to get over. So that's why at the store, they remain unreacted, that you have the peroxide, you haven't converted it into oxygen gas yet. But as soon as you add a catalyst, so in this example, HBr is the catalyst, you're adding bromide and H+, but your blood could also be a catalyst to this reaction. Look, now it's a multi-step mechanism. It's actually boom, boom, 2 steps. Okay, when your blood, or in this case HBr, is being a catalyst to this reaction. So you see here that Br- and H+, that is your catalyst. Because if you look at the product side, look, the catalyst shows up again. And so what you get here are intermediates. Br2 is our intermediate in our reaction. You can look at the full, this one's kind of hard to see because it's all written in the reaction coordinate. But what you see here is that Br- is a reactant, then a product, so it's a catalyst. H+ is also a reactant, then a product, so it's also a catalyst. But Br2 cancels out. This is an intermediate, right? Because it's produced then consumed here, right? So the idea here is catalysts provide a new reaction pathway that overall lowers your activation energy. It's going to be a lot easier to go over 2 smaller humps than it is to go over 1 large hump. And that's the idea of a catalyst. Okay, enzymes are our body's catalysts to catalyze unfavorable reactions. Enzymes, sometimes they're homogeneous, sometimes they're heterogeneous, depending on how big the enzyme is. But the idea here all comes back to the Arrhenius equation, that enzymes you can think of is this substance that brings together reactants so they will react with one another and then make the products that we want. So how enzymes speed up reaction is they bring your reactants close together. They orient them so they can make really efficient collisions. And so what that does is increase A in your orientation factor in your Arrhenius equation to make your rate constant increase. But it also changes and weakens the bond energy of your reactants. So what that does is decrease activation energy. So enzymes are just our body's way to make certain reactions go faster. In biology, they tend to not use chemical terms like reactants and products when it comes to enzymes. So instead, they use terms like substrates and active sites. So the active site on the enzyme is just the spot at which the reaction, the catalyst happens, the catalysis happens. Substrate is the same word as reactant, right? So they just say, oh, these things are reacting with one another. They're the substrate, but it just means reactant, all right? They also talk about enzyme substrate complexes. This is the same thing as an intermediate. When the enzyme brings together those reactants and it makes the intermediate to catalyze the reaction, biologists call it the enzyme substrate complex, but it's basically just an intermediate that occurs right there between the 2 different steps. So those are enzymes. I don't know if you've noticed, but I don't like living things. And so that's my attempt at biology, but what I do like are cars. And so another example of catalysis is what happens in our cars in a catalytic converter, okay? So enzymes is an example of our body's way to catalyze reactions. They're usually homogeneous in nature because everything is dissolved in water. But in a catalytic converter in your car, this is an example of heterogeneous catalysis because that catalytic converter is actually a solid. It's a solid that's made up of rare earth metals, platinum, palladium, right? So these solids are what catalyze what's happening is a redox reaction between some of the noxious gases that come out of our tailpipe in our vehicles. So after the EPA passed many acts to reduce car emissions, that's where catalytic converters became very important. But what you see here is that the catalytic converter contains about 5 grams of platinum, palladium, rhodium, really expensive rare earth metals. I looked up on the internet, and based upon the composition of a catalytic converter, just off of the metals, the rare metals in it, it's worth about $200, $300 just in how, like 5 grams of rare earth metals. If you go on the black market and try to sell a catalyst, a hot cat, like if you stole one or something, it goes for about that much, because it's those rare earth metals are what make catalytic converters expensive and valuable. And so that's why that's a concern, because a lot of people have been stealing cats off of cars, because yeah, it's like $300 to $500 worth of just rare earth metals just sitting right there underneath your car. And so we'll talk about catalytic converters when we get to electrochemistry, but some ideas behind a catalytic converter is because of its heterogeneous nature. If you ever cut one open, you would see that there's a honeycomb shape on the inside. All right, and this is to allow the gases to pass through that solid surface. It increases, the honeycomb shape increases the surface area for catalysis to occur. So that's why it's a porous surface for a lot of gas solid interaction to happen, because the catalysis that's happening is trying to convert gases into less noxious materials. What we also see in catalysts is that they basically will only improve reaction speeds, catalytic activities at certain temperatures. High temperatures are when catalysts are most effective. And again, this has to do with the Arrhenius equation. High temperatures lead to faster reactions. So, you know, the idea is, you know, before you like start your car on like a cold winter's day, oftentimes they say, oh, let it warm up a little bit. And that warming up has an effect on how effective your catalyst is in converting those noxious fumes. You want to get up to temperature before the catalytic activity happens. And then the last idea here, so yeah, temperature increases, K increases. The active surface can be spoiled by lead. And so if you go to the gas station and you buy like regular gasoline, they call it unleaded gasoline, because before, prior to the forming of the EPA, they used to put lead into gasoline, and that lead actually spoils that catalytic surface. And so if you do get lead into your catalytic converter, it renders your catalyst useless, essentially. All right, so those are catalytic converters. So fun stuff. So it's a question like this that will show up on your exam, talking about catalysts, intermediates in relation to mechanisms. So here I have a 3-step mechanism. Okay, I don't tell you what the slow step is because it doesn't matter in the context of this question. I want you to be able to identify what kind of substance is each of these you know, things. So what is A in this reaction? Is it a catalyst, an intermediate, or is it neither? So notice how things cancel out in this reaction. So actually, let's start with the first question. What is the overall equation in this reaction? So we got to add up everything and cancel out what we need, noting how they cancel out. So we get C cancels, I think. What else cancels? D cancels. And then what else cancels? B can't B? Yeah, but does it cancel the same? No, it cancels different. Yeah, okay, there we go. So we see that this reaction is 2 A's become an X, and that's it. So A is a what? Is it a cat? Is it intermediate? Nope, it's actually a reactant, that's all. So it's just neither. It's a reactant. Okay, what is B? It's a catalyst because it's a reactant, then a product. You add it, then it's made at the end. C, intermediate. D, intermediate. X is a neither. It's a product. Perfect. That's it. All right, so that's basically something I will assess to you on the exam. Okay, so that is the end of chapter 14. So remember, there are 2 parts to chapter 14, but I'm going to be nice. All right? So technically, the second part of chapter 14 would be due on Monday, but I'm going to wait until after midterm 1, okay, because it's going to be on midterm 2, all right? So do look at those due dates. I'll put in my recap email about, remind you of due dates. But basically the 2 homework assignments for midterm 1 are due on Monday. We'll wait off for these ones until the next Monday, but it doesn't mean that you can't start them, okay? It's just when the due date is there, okay? All right, so let's do the demo, and I think I'll have to end there. Okay, so chemical kinetics. So I want to remind you, here's 2 different reactions. Which one will go faster, A or B? B, why? It's all gases, yeah, so B is going to go faster. Okay, so it's going to go faster. So which one, just like, let's think about it. Which one do you think the activation energy, the particles interact easier, so the activation energy is low? Between solids or between gases? What do we think? Okay, so if the gas reaction goes fast, what does that say about its activation energy? It's low, yeah, so if this reaction K is big, that means its activation energy is low. So that means for A, because it's between 2 solids, you just told me that this reaction is slow. It has a very low activation energy. So what does that say about its, it has a low rate constant. So what does that say about its activation energy? It's probably high. Okay, perfect, because I'm going to do this demo. Okay, we're going to blow some stuff up because I'm going to do 2 different exothermic reactions. One of them is between gases. We already saw this, all right? That's the hydrogen balloon reaction, hydrogen gas, oxygen gas. Should this reaction go fast or slow? It should go fast because all of its gases. Also, its activation energy is low. So note how I have to get the reaction started. Versus the second reaction I'm going to do, what are the physical states of the 2 reactions or reactants in the second reaction? They're both solids, yeah. So we're going to see this second reaction. It's also highly exothermic, but how is the reaction speed? It's going to be slower. It's going to be slower. It's still going to happen. It's just a little bit slower. And note here that there's 2 solids involved. It's a slow reaction. It has a high activation energy. So note how I have to get the reaction started. All right, so we'll do reaction 1 first. Okay, reaction 1 is between the gases. It's going to go quite fast. So don't blink or you will miss it. But you'll definitely hear it, right? So let me get safe. And I'll remind you, we did this on the first day of class as well. It's very, very loud and everyone has to cover their ears or put headphones on because I don't want to be the reason you have early onset tinnitus or tinnitus or whatever because it's really loud. Okay, all right. So fast reaction, low activation energy. It's quite easy for me to get this reaction started. So let's everyone do the ears. We're going to do the gas reaction first. Okay, ears. You guys too. Ears. Everyone. Okay. All gases. Don't blink. Okay, was that fast? It was fast. And was it quite easy for me to get that reaction started? It was. Yes. Okay, so now let's do the all solid reaction. It is also quite exothermic. It's really cool. But notice how much harder it is for me to get this reaction started. So what I have in this flower pot is rust, so iron oxide solid, and aluminum solid. And I didn't do it, someone else did it. They grinded them together. Okay, but in order for this reaction to start, I have to light a fuse. And what that fuse is a strip of magnesium. So I'm going to light the strip of magnesium to get the reaction started, but it's not actually the reaction. So, okay, let's do this. And notice how I have to get it started. I have to use a blowtorch, then light the fuse. But for this one, I just used a little candle to get it started. And that has to do with the activation energy. So this one, you can blink and you'll still be able to see the reaction happen. So let's hope this happens. Oh, I should move my iPad. Oh! Okay. Sometimes it happens again. Okay, so that glowing that you see is actually molten iron, because if you look at the product there, it's iron solid is a product, and it's literally molten and, you know, like glowing like lava does, because it's so hot. So in that second reaction between solids, it was slower, right? Like you could blink and it still happened, and it took a lot of energy for me to get it started because it was between solids. So it has to do with not only reaction rate constants, but also activation energies due to the states of matter. So that's chapter 14. That's my favorite demo. So which one do you like more, the gas one or that one? That one? Yeah, that one was big. That was big. Okay, all right. So that's it. We'll just end right there. Monday, we're going to jump right into chapter 15 and do some review. Have a good weekend. Whew. What's up?